3.5 is rational equations, rational inequalities, and rational functions. First thing we're going to take a look at is an example of a rational equation. So we have 2x plus 3 over 2 minus 3x over x minus 4 equals x. And then we need to make a note that x cannot equal 4. Since x minus 4 is a factor in the denominator, 4 would cause division by 0, so it is not possible. We're going to look for all real number solutions. Now, in order to make this equation a little easier to handle, we're going to multiply by the 2 in this denominator, multiply by the x minus 4. We need to do that to all terms. Once we do that, we will have 2x squared plus 3x minus 8x minus 12 minus 6x on the left. And then if we did that on the left, we need to multiply by that same thing on the right. So we'll have 2x squared minus 8x. Then we need to carefully combine like terms. And we end up with negative 3x minus 12 equals 0. Solve that linear equation, we get x equals negative 4. Rational inequalities. So in this example, we have 2 over x minus 3 plus 1 greater than or equal to 0. The first thing that we want to do is get a single rational expression. So we need to find a common denominator and create a single rational expression, in this case greater than or equal to 0. And we also want to make a note that x cannot be equal to 3. It is not included in the domain. So the first step to solving after obtaining a single rational expression is to find critical values from setting the numerator equal to 0 and denominator equal to 0. So numerator equal to 0 gives us x equals 1 as a critical value. Denominator equals 0 gives us x equals 3 as a critical value. Critical values are where we separate the number line. So we separate the number line at 1, we separate the number line at 3. Remember that 3 cannot be in the solution set. Then we need to identify the intervals. Negative infinity to 1 with a bracket. Since the original has a greater than or equal to, a bracket is appropriate there. Bracket 1 to 3, parentheses next to the 3, since 3 is not included in the domain. And then parentheses 3 to infinity. Then we're going to pick a test value in each interval, plug it into the original, and see if we get a true statement or a false statement. When we plug in x equals 0 from this interval into the original, we get a true statement, which tells us that negative infinity to 1 is part of the solution. Bracket 1 to 3, parentheses, we tested x equals 2 in the original. We got a false statement, so this interval is not included in the solution. And then parentheses 3 to infinity, we tested x equals 4 in the original, got a true statement. So parentheses 3 to infinity is part of the solution set. So this interval and this interval are unions together in the solution set. Rational functions. A rational function is a polynomial divided by a polynomial, and any values that cause the denominator to be 0 are not allowed in the domain. The reciprocal function is 1 over x. Here's what the graph looks like. It has a domain that does not include 0 because that would cause division by 0. This function is decreasing on its entire domain. It is continuous on its entire domain. There is a discontinuity at x equals 0, so the interval of continuity is the same as its domain. The range is negative infinity to 0, union 0 to infinity, because it is not possible for a rational function with a constant in the numerator to be equal to 0. All other numbers are possible outputs. This function is odd, meaning that negative f of x equals f of negative x. It has origin symmetry. Then to signify the domain error at x equals 0 on the graph that is known as a VA, at x equals 0, vertical asymptote, the HA tells us the y value that the graph flattens out at as x approaches plus or minus infinity. So as x approaches positive infinity, the graph flattens out at y equals 0. As x approaches negative infinity, the graph flattens out at y equals 0. That's called a horizontal asymptote. Then we just want to recall graph shifting properties from previously in this semester. We can shift the reciprocal function up, down, left, and right. So in this example, we have a -3 inside the parentheses. That's going to shift right 3, and then a +2 on the outside of the parentheses. That's going to shift up 2. The next function we're going to take a look at is 1 over x squared. It has a VA at x equals 0 as well, has an HA at y equals 0. It is increasing on negative infinity to 0, decreasing on 0 to infinity. The domain and range are the same as the reciprocal function. There's a discontinuity at x equals 0, and it is continuous on its entire domain. This function is even, meaning f of x equals f of negative x, and it has y-axis symmetry, so if you folded it vertically, the graph would be on top of itself. Vertical asymptotes. For x minus k, a factor of the denominator, and not a factor of the numerator, x equals k is a vertical asymptote. And the behavior at VAs, if the VA has even multiplicity, the graph goes the same direction on either side of the VA. If the VA has odd multiplicity, the graph goes opposite directions on either side of the VA. A hole in the graph. A hole in the graph exists at x equals k if x minus k is a factor of the numerator and the denominator. HA, horizontal asymptote. The first case is if the degree of the denominator is strictly greater than the degree of the numerator. There is always an HA at y equals 0. The next case is that if the degrees are equal, the HA exists at y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. And remember that an HA tells which y value is being approached as x approaches plus or minus infinity. Then we have what's known as an oblique or slant asymptote. And we're going to look at one case for this OA. If the degree of the numerator is 2 and the degree of the denominator is 1, an OA exists at y equals mx plus b, where mx plus b is the result from synthetic division. So let's take a look at this example and find the VAs and HA. We have f of x equals x minus 1, x plus 3 in the numerator, x plus 1 squared, x minus 2 in the denominator. So on the VAs, x equals -1, multiplicity 2 comes from x plus 1 squared in the denominator. And then x equals 2 comes from the factor of x minus 2 in the denominator. Now on the HA, the degree of the numerator is 2. Since if you added up the exponents from those factors, you would get 2. The degree of the denominator is 3. The rule says that since the degree of the denominator is strictly greater than the degree of the numerator, the HA is at y equals 0. On this example, we have a hole in the graph at -3 because x plus 3 is a shared factor in the numerator and denominator. That creates a hole in the graph. The only VA on this one is at x equals 5, and that comes from x minus 5 as a factor. And on the HA, degree of the numerator and denominator are both 2, so the rule is that the HA exists at the ratio of the leading coefficients. Leading coefficient of the numerator is 5, leading coefficient of the denominator is 3. So the HA is at y equals 5/3. On this one, we're going to graph x plus 6 over x plus 2. First thing that we want to do is find the y-intercept, so f of 0 gives us 3. And on the x-intercept, provided there is no hole in the graph, that's the same as just setting the numerator equal to 0, so we have x plus 6 in the numerator, so -6 with multiplicity 1, so we need to keep that in mind because it will cross the x-axis at -6. So -6, 0 is the x-intercept. Then we're going to find all of the asymptotes. The denominator has an x plus 2 as a factor, so x equals -2 is the VA, and the degree of the numerator and denominator are both 1. So the rule is that the HA exists at the ratio of the leading coefficients. The leading coefficient in the numerator is 1, leading coefficient in the denominator is 1, so the HA exists at y equals 1. Then we put that information on the graph and draw the function accordingly. So at the VA, there's odd multiplicity, and the y-intercept is positive, so the graph has to be up here on the right-hand side of the VA, and it's going to flatten out at y equals 1. Now, since the multiplicity is odd on the other side of the VA, the arrow has to be going the opposite direction. And at -6, the multiplicity is odd, so it's going to cross. And then as x approaches -infinity, the graph flattens out at y equals 1. On this one, we're going to give the equation of the OA. So we set up the synthetic division. We have 3x squared minus x plus 4 over x plus 2. Set up the synthetic division. And we get 3x minus 7 from the synthetic division. And that's the equation of the OA. So looking at the graph, as x approaches plus or minus infinity, y is going to tend to follow 3x minus 7. On this one, we're going to give the function by using the graph. So we're going to take the information from the graph and then put it into the function. So this 10, 0 as an x-intercept means that x minus 10 is a factor in the numerator. The VA at x equals -1, where the graph goes in opposite directions, would be an x plus 1 with odd multiplicity, so an exponent of 1 as a factor in the denominator. Now we've got an x equals 2 as a VA, and the graph goes the same direction on either side of the VA, so x minus 2 would be the factor, and that factor, that k value would have to have even multiplicity, so I mean we would need an exponent of 2. Now there's an HA at y equals 0, so that means that the degree of the denominator is strictly greater than the degree of the numerator, and that is accurate. The degree of the numerator is 1, the degree of the denominator is 3, so that matches up. And then we want to check to make sure that our y-intercept matches the graph. So when I calculate f of 0, I get -5/2, and that matches the graph. So our function is x minus 10 over x plus 1 times x minus 2 squared.